So here's an important kind of problem that you're definitely going to see on your AP test. I've never seen an AP test that didn't have a multiple choice question where you asked to either, given the derivative, the graph of the derivative, find a graph of the original function, or given a graph of the original function, find the derivative. So we want to start to understand what we could expect to see in the graph of a derivative given the graph of an original function. So this is from page 107 in your book, so I copied both parts. I only put half of this on your paper. Over here in this column, I have 4 functions, and I've been told that these functions here on the right-hand side are the 4 derivatives of those 4 originals from the left. So our goal is to match up each function on the left with its derivative, which is on the right. Here's my thought process. You'll probably develop your own, but I hope you'll consider starting with this idea. So I'm going to just look at this first function on this list. I notice that this function is decreasing when x is less than 0, so on the left half of the picture, to the left of the vertical line that is the y-axis. And the function is increasing to the right of the place where x equals 0. That means to me that my derivative should be negative to the left of 0 and positive to the right of 0, to the right of the place where x equals 0. So I'm going to look at my answer choices, and I notice of all the answer choices, answer choice B is the only one that is negative, that has negative y values, which are the slopes, at the place where this original function was going downhill. So remember, downhill, negative slope. So I say that the first graph here, which I think is problem 13 in your book, matches up with graph B. Now I'm going to move on to the second graph, which I think is graph 14. I notice that this function always goes uphill. So there's a point here in the middle at the place where x equals 0. It seems like it flattened out for a second, but there's no place where the function goes downhill. That tells me my derivative should never, ever, ever be negative. Well, I notice there's negative values here and negative values here. I'm going to rule them out. I notice this function has no negative outputs. There are other places we could check. I say that this graph matches choice A, and I just want to call back into your memory. There was a point in class today where we took the derivative of the function f of x equals x cubed. And my belief is that that function closely resembles the graph of x cubed. Do you remember what the derivative was? It was 3x squared, which tells me the derivative of a cubic is a quadratic. Or at least the derivative of x cubed is 3x squared, which is quadratic, which matches this, which is shaped like a parabola. All right, so what if I wanted to try this next one? Let's see. So this function, I'm just going to start here at x equals 0. I notice this function goes downhill and then uphill to the right of x equals 0. If I start at x equals 0 and I move to the left, the function was coming uphill but came downhill right before. That means to me that my function is, that is, my derivative is going to be negative, since f of x was going downhill to the right of x equals 0, the derivative is going to be negative and then positive. Oh look, both my answer choices meet that requirement. All right, what if I try this guy? So let's try this approach. We're going to look at this last function. I need a new color. This last function goes downhill, then uphill, then downhill, then uphill. That tells me my derivative to the left of x equals 0 should be negative, then positive, then negative, then positive. So does that narrow my choices? This function is negative and then positive, and then negative and then positive. Part D, that's positive, then negative, then positive, then negative, then positive. So it's got one too many pieces there. Oh, I see what's going on. This little tail here, that was an extra uphill section on number 15, which corresponds to this extra positive section on this graph. So one way to choose is here we decided was more like letter C, and this one is like letter D. We're going to learn some more techniques that we can use to relate graphs of functions to the graphs of their derivatives, but that would get you your 4 answers here. This last little chunk of problems is just to help us make the connection between derivative and slope. If we have a function rule, if we've been given a formula for our function, we can use that definition for derivative that we've been using to find a rule for the derivative. Or we're going to learn some shortcuts coming up really soon too. If we don't happen to have a function rule for a function, then the best approximation we can give for the derivative is slope. And if we don't have a way to find instantaneous slope at a single point, our next best option is to find the slope of the secant line. So this is just some practice. You saw this already a little bit in chapter 2 about how to use the average rate of change of a function to compute an approximation for the derivative. This is a very common question on the AP test. It doesn't actually take any calculus, but it does take understanding that idea that the rate of change of a function is the derivative. Derivative means slope, and in a case where you can't compute exact slope, approximation of the slope can be made using average rate of change. Also, you'll notice that now I'm going to be able to use this notation for you, and you'll know that that means derivative. So we'll do number 1 together, and then you can try the rest on your own, I think. The temperature in degrees Celsius of the water in a pond is a differentiable function of time. That means I promise that the derivative exists. There are some functions that don't have derivatives, and I wouldn't be able to ask you this question. The table shows the water temperature recorded every 3 days over a 15-day period. Can you find an approximation for W prime of 12? Show the computations that lead to your answer. So notice if you want a full credit on the AP test, you would say that W prime of 12, I'm not going to be able to give an exact answer. Exact answer means, derivative means instantaneous rate of change. A change like where the distance between the 2 points you're using is 0. I won't have that, so I have to show that I'm going to give an approximation. So you'll have to use those squiggly equal signs to show that we're approximating our answer. But notice they were very clear they were expecting an approximation. So I would choose here 2 ordered pairs. This is like the one problem I've seen them where there are a couple of different options you could use. I might choose 2 ordered pairs on either side of 12. You could use 12 and 15 or 9 and 12, include 12 in your answer. But I'm going to use 9 and 15. I'm going to say that's like W of 15 minus W of 9. Sorry, I can tell now that you can't see that, but that's W of 9 over 15 minus 9. W of 15 was 21 minus 24 all over 15 minus 9. The units on 21 and 24 are W units. Those are degrees Celsius. And units on the 15 and 9 were units from the T column. Those are days. Make sure you give units with your answer. This is going to be -3 over 6, which is the same as -1 over 2 degrees Celsius per day.